In this video, I want to explain convolution mathematically using very visual descriptions. And this is going to really help our understanding of signal and image processing and also serve well for understanding some of deep learning as well. Okay, let's get underway. These are the three forms that I want to explain in this video. I'll start off by this discrete case here, relate it to the continuous case, and then finish with what I feel is the best understanding of all for convolution, which is the matrix vector terminology. So what we've got then, in general, is some kind of linear system, and we're putting in some input function f on the left-hand side here, and getting some output g on the right-hand side, some output from the linear system. Concretely, that linear system could be, for example, a sound system doing audio digital signal processing, and there'll be some digital waveform, for example, going into this audio DSP system, and then we'd have some output here, which I'm not showing because it would depend on the particular processing that system did. For an imaging device, this could be also regarded as a linear shift invariant system, and in general, there's going to be some kind of scene that is photographed, of course, and then we'll get some output which will never quite directly relate with the input because of the imperfections in the system, in the linear system. Right, so to really understand convolution, which of course is describing a special type of linear system, ones where the response is so-called time or shift invariant, we're going to need to understand what happens when we put in what's called an impulse. We call it an impulse when we're dealing with time-based signals, like for example, audio DSP, or we'll call it a point if we're dealing with imaging systems, but in general, we could call it a delta function. That's probably the safest all-round general description. So we need to understand crucially what happens when we put a delta or point input, impulse input into our linear system. What we're going to get, I'm just giving an illustration here of an example. What we're going to get is what is known as the impulse response function, or the point response function, even the point spread function, or in general, what's called the convolution kernel. In other words, when we put a point or delta into our operator, into our linear system, we get some response that we're going to be calling the response function. Okay, I'll label that as H in this video. To give a concrete example, imagine this is a very crude description of an impulse input, a digitized one here, going into a sound system, audio DSP. Then we could get some response that looks like this, and this would correspond to an impulse response function that is in fact doing some kind of bass boost, some kind of frequency modification of the input to, for example, exaggerate the low frequency content. For an imaging device, that impulse input, that delta function would actually be a point. Think of that as like a point of light in the night sky, as a point input to our imaging device, our linear system, and then we're going to get some point response function or point spread function, PSF, as shown on the right-hand side. Again, notice it's not a direct match for the input, and this is why we have this notion of the system response, which in general doesn't match the input. Right, so now what I'm going to do is build up the mathematics of understanding how to describe any output, any result, any output from this linear system. For example, any output image or any output sound signal, for example. And so to do that, I'm going to be using just an illustrative example of a response function. So I'm just picking this kind of arbitrary waveform here, and I'm just going to sample that at 5 different points. So here I'm going to be having a sampling location n, and I'm going to be visiting location 0, 1, 2, 3, and 4. Okay, I've got this first sample a little bit off the origin just for simplicity here, so we can actually see the amplitude of the sample. And so I'm just going to be working with a simple convolution kernel or impulse response function that is just a value of 3, 2, 1, 0, 0. And I'm just going to stack those values into a column vector 3, 2, 1, 0, 0 and label that as H. Okay, now the key thing to understand is if we've captured the response of a linear system to an impulse or point input, then we are well able to explain the system's output for any arbitrary input, because any arbitrary input function can just be regarded as a collection of impulses or a collection of points. Okay, so here I'm giving another illustrative example here. I'm just using a sequence of numbers, 5, 3, 7, 1, 2, to represent arbitrary values for an arbitrary general input function. But for illustration, I've got to concretize that into some of these numbers. So I'm using 5, 3, 7, 1, 2 for a general input function f. And so I put that in a column vector f there. Right, let's see what happens when we present that input function to our linear system. So what we're going to do then is consider the first impulse, which has got amplitude 5, and we know that the system has an impulse response function or a point response function that we're just showing by this example h here. So an impulse at the origin, okay, gives us the impulse response function located from the origin outwards like this. And so the output to that first delta function or impulse input is just going to be the amplitude of that impulse, which here is 5. When we do the regular impulse, of course, it's just unit amplitude, and that gives us the impulse response function. But here, for an arbitrary input now, we've just scaled the impulse by some amount 5, and so that is the scaling factor, which of course in general is just given by the input function f evaluated at that first sample point, so that's f of 0. So here's n equal to 0, and there's the value f located at n equals 0 equals to 5. So we just take 5 times the entirety of that response function. Okay, so impulse input gives a response function. If we now have 5 times the height of that impulse, then we correspondingly get 5 times the height of the response function. So that's f of 0 as the scale factor or amplitude or coefficient of the response function h of n. And I've just put in here the fact that it's not shifted. So minus 0 just means it's just h of n. It's not shifted at all. The response is just from the origin. Right, let's go to the next impulse, the next, if you like, sample in our input function f. This is now located at n is equal to 1. We've got a value of 3, so we take a value of 3 and multiply it by the entirety of that impulse function, but it's now shifted, so I should have a 1 here. I'll show that in a moment. So we're taking h of n, the impulse function, shifting it to the right by 1. We're shifting it to the right by 1 because we're considering an impulse that is shifted to the right relative to the origin by 1. Okay, so the response to that is just going to be the impulse response there, just scaled by the amplitude, which is 3. So 3 times 321 is just going to give us our 9 and 6 and 3. Okay, 96300 would be the response. Okay, so it's a very simple principle of, it's called homogeneity of a linear system, where if you scale up or down here, you scale up or down the output. Right, next impulse. Okay, so that's a value of 7. So we get 7 times the impulse response function, but now again shifted to the location of that impulse. We've got n equals 0, n equals 1, n equals 2. Okay, so we've got the value of the input function f evaluated at n equals 2. That's the scale factor for the response function h of n shifted to the location of that impulse. And so we've got 7 times 3 is 21, and also likewise the others are scaled as well. Next impulse, same kind of reasoning. We just get the value of the input function f evaluated at n equals to 3. That's the overall scale factor for a response function h of n shifted to the location of that impulse, and likewise again for the final impulse function. Right, so we can see here we've decomposed the input function into separate deltas or separate impulses, and then we've just looked therefore at the corresponding outputs to all of those separate impulses. Now, this is a linear system, and so we've also got the property of additivity, which means we can just simply sum those outputs to get the response to effectively a sum of shifted scaled delta functions, which is what this input function is. Okay, that's all there is to convolution. We're just going to be adding together all of those individual outputs. So again, I've kept the same notation before, and I'm just saying we just sum them all together, and that's going to give us the overall output of that linear time or shift invariant system. And so all I've done is just mathematically sum all of these values. I've just gone from n equals to 0, 1, 2, 3, and 4, and just looked at all the values, just scanning down, if you like, the columns here, adding them all together, and that gives me the overall output. Okay, so if I do the sums there, you're welcome to check. The first one is 15, because there's nothing here, nothing here, nothing here, nothing here, and so on. You get a value of 15. Do it for all of these, just sum down the columns there, and you'll find you get this result. Now you'll notice that I have cropped the output, and that's just because I also want to move on to a matrix example in a moment, where I'm going to be limiting the number of sample points. So we'll revisit that issue presently, but for the moment, 5 sample points in the input vector f, 5 sample points for h, 5 sample points for the output g. Therefore, I'm cropping out those samples. Right, now let's get to the mathematics, that discrete version of convolution. You could look at these simple descriptions. It was just a scaling of the impulse function, just shifted to the location of where that scale factor came from. So in general then, we've got the input function value f at location n equal to k, and so therefore that is the overall scale factor, just scaling up or down the impulse response function. That's the scaling factor for h of n shifted to the location k of that impulse within the input function f. Okay, so therefore to get the overall output, as I've been showing here, all we've got to do is just sum together all of those responses that have just been scaled and shifted. Okay, and so just to explain here that I'm using k as a, if you like, a dummy variable of summation. So here k needs to visit all of the locations in the input function f, and so here k would go 0, 1, 2, 3, 4, but in general we can cover every conceivable sample point. So here I'm just summing all the values of k to visit all of, visiting all the values in the input function f, and then shifting h of n to all of those possible locations of the impulses, and then just summing together the outputs. That's all it is. And now this links very obviously with the continuous form of the convolution integral, where here I've got f of k is now replaced by f of t prime. So k was my index of summation. Here t prime is my integration variable. So just like k here allowed me to visit all of the values of the input function f, here t prime allows me to visit all of the values of that input function f, and then each of those values behaves as a scaling factor for the response function h of t shifted to the location of each of the impulses. Okay, so here's the amplitude of the impulse, amplitude is f, of the impulse located at t prime, and so we've got to do the response function at shifted to that same position t prime, and then it's just amplified by the input function at that position t prime. And then of course we sum them all up, and therefore here we integrate them all up, all of these responses. So here the sigma has gone to the summation, the integral here over dt prime, because t prime here is corresponding to k in the discrete version. Right, okay, let's get now to matrix vector, which I think is going to be the very helpful version for everyone to understand. So what I've got then is my input function f as before, so it's just example values 5, 3, 7, 1, 2. Here it is at the bottom of the screen as well. And then what I've done is take my impulse response function, my point response function, my convolution kernel. Here again, it's just the example of 3, 2, 1, 0, 0. And you'll see that I've just put it in that first column of the matrix. And then in anticipation of exactly the process I've just gone through, I've then shifted it to the right, okay, and just created new columns of this matrix. So here I've taken 3, 2, 1, 0, 0, shifted it. So again, 3, 2, 1 there, 3, 2, 1, and so on. And I've just cropped the output again here, because this will allow us to very simply get the output of convolution just by the following process. There's the 3, 2, 1, 0, 0 of the convolution kernel. The following process is all that convolution is doing. We just take the value of the first impulse function here, so n equals 0. We get the value f, and it's a value of 5. So we take 5 as a scale factor for the entirety of that column of the matrix, in other words, the entirety of the response function. And so we take 5 times this, and so that's 15, 10, 5, 0, 0, which is graphically what we saw before. And then we visit the next impulse function, which is a value of 3 located at n equals to 1. And we take that value of 3 as a weighting or a scale factor for the entirety of that shifted convolution. kernel. And so it's 0,321 multiplied by 3 gives us 0,963. And we just repeat the same process. We get to the third sample point in the input function f. So it's 7 times that shifted copy. And then 1 times the next shift, and so on. We just follow that all the way through till we get to the last sample point here. So this is a value of 2 times that shifted response function. So it's 2 times 3 is 6, 3, 2, 1, and so it's 6, 4, 2. And again, I've just cropped the results here. And you'll notice that this is a very, very simple process. There's no reversal, no flipping of kernels, none of that is going on whatsoever. All I'm doing is decomposing my input function into a collection of impulses or delta functions at different amplitudes and using those as scale factors for the response function, where of course the response function needs to be positioned at the location of each impulse that I'm considering. That's all that's going on here. And this is what I call input-driven understanding of convolution. Okay, and for this particular convolution kernel, just the form that I've used, and you'll see why I've used this in a moment, we can see that, so for example, when we finished here, we had this last input value here, and so the convolution kernel here was showing us that the output is affected immediately at that same sample point, n equals to 4, but it also impacted the next 2 time points as well, okay? And that's just an observation because it will help us with what we're about to see next. But this is what I call input driven. Just visit each impulse or each delta in the input function and then look at the response to each, sum them all up, and you're done. Okay, so that should give us, I hope, there we go. If we do this sum of all these outputs, we get the result of the convolution, the output G. And so this is matrix vector multiplication understood simply as a weighted sum of columns. Each input element in the vector f behaves as a weighting factor. Imagine taking the 5, 3, 7, 1, 2, placing it along the top there, and then as scale factors for each of the columns, and then summing them all together to get the output there. And so that's just depicted here. So this is the same result as what we've seen before, but now in a matrix vector form. But now I want to get on to this, which is another way of understanding convolution, which is what I'd call the output-driven understanding, which is what most people seem to choose when they explain convolution. But as a result, I find not many people properly understand convolution. So let's take a look at what's going on here. So now we're just focusing on one particular example output sample. Okay, so this is output vector G. And we've got the 5 sample points, n equals 0, 1, 2, and n equals to 3 is this value of 20. And we can see that by the other understanding of matrix vector multiplication, that this value here is just obtained by taking this row vector of the matrix and taking it in scalar product with the input vector. Okay, so let's now take a look at this row vector. There is that row vector. It's 0, 1, 2, 3, 0, 0, 1, 2, 3, 0. And you'll notice that this is a reversed version of the kernel that we've been dealing with before. So that's why we've got h of minus k. It's now flipped. But then also, because of course, as we've been going along these columns here, we've been shifting the response function. As a consequence as well, this reversed kernel doesn't sit at the origin. It's not 1, 2, and then 3 at the origin. It's actually 0, 1, 2, 3. In other words, it's been shifted to the right by 3 sample points. Okay, so let's just check that. So it'd be 0, and then 1, 2, 3 sample points. Yeah, so it's h of minus k plus 3. And so what I'm explaining here is exactly the same as what we've already seen, but just looking at it at a different way for exactly the same calculation. Because my preferred way of understanding convolution is the input-driven approach that I've just been explaining to you, which is extremely trivial. Just each impulse gives a response. Each impulse is scaled, and so you scale the response, and then any input function is a collection of impulses at different amplitudes. Therefore, the output is a collection of response functions of different amplitudes. Very, very simple. But anyway, let's just show that alternatively, you can get exactly the same description using this approach, where we've got to flip the kernel and shift it, and then do a point-by-point multiplication, and then sum up the result. That's a scalar product. So let's take a look at that then. So we're saying the output G at element 3, n equal to 3 there, is just given by the input function f of k. This is input function f of k, where we're using k to just access all the elements, the kind of dummy variable of summation. And we're accessing each of the locations in the input vector f and using them as scale factors for the response function h, which now, in this description, we can see we've got to have the negative, in other words, the flip of that kernel h, and then shift it to the location of the output value that we're seeking. Okay, so here is f of k here. So f of k is just shown here. H of 3 minus k is shown here. So we do the point-by-point multiplication, just do a scalar product, and with 0 times 5 plus 1 times 3 plus 2 times 7 plus 3 times 1 plus 0 times 2. In other words, just take these in product, just take all the values here, point-by-point multiplication, and then sum up the results. And so in general then, we could write it in this form here. Instead of focusing on just the sample point at n equals to 3, we could pick any arbitrary n, and so I've just replaced 3 by the arbitrary choice n there. And here then we get our description of what I'd call the output-driven understanding of convolution, where now we can see, in fact, that the output value here not only relates to the corresponding input value at that same sample point, but also it shares the consequence of previous time inputs as well that have contributed to that moment in the output. So that's the output way, the output-driven way of understanding convolution. And that output-driven approach, I'd say, is more natural for sound-based audio DSP kind of systems. That can be a useful way of understanding those systems. It's up to you, you can view them either way. I much prefer the input-driven example because I'm more into imaging sciences, where you just present points to an imaging system and then you get point response functions, and you just can just model the output of any arbitrary input as just a summation of response functions. You don't have to do any of this flipping or reversing, none of that. It's just a very simple process. And here then I'm just relating that output again to the continuous version of the integral, and hopefully you can see the sigma goes to the integral sign here, summing over k, and here instead we're just integrating over t prime, where t prime is allowing us to access all the positions, all the time points in that input function f. And then of course we're taking h of t and shifting it to the location of each of the impulses being considered in f. Sum them all together and that gives us the output. Right, so as touched on before then, this matrix that I've been forming, I'll label it as capital H. It's just a collection of shifted copies of that kernel H. So output vector G is equal to capital H times input vector F. Right, just to finish then, remember that cropping that I was doing? Well, that has resulted in, because we had excess values here that I just clipped, cropped, removed. That's resulted in this matrix H being called a Toeplitz matrix. So I should have an equal sign here, of course. And that's just named after the German mathematician Toeplitz, where all you have to do is just scan from left to right the diagonals, and it'd be a constant value on all those diagonals. That's a Toeplitz matrix. However, for convolution to be properly understood, you should be using a circulant matrix, because then that links beautifully with Fourier-based methods when you use the convolution theorem and so on, where with the discrete Fourier transform you have periodically repeating discretely sampled functions. And so for that case, instead of cropping off the values, we need to actually wrap them around. So 3, 2, 1, instead of dropping it, we wrap it around back at the top. 3, 2, 1, wrap it around back at the top there as well. And that would be called a circulant matrix, which is a special case of a Toeplitz matrix. So I hope with this video you've now got a very firm understanding of these three versions of convolution: the continuous, the discrete, and the matrix vector, where the continuous form is the one that's most commonly seen, where you can just say that the input function f, you just visit all the locations t prime inside that input function, use it as a scaling for h of t, where of course each of the h of t's needs to be shifted to the position that you're considering in the input function and sum them all together to get the output. But I prefer the matrix vector notation, and I prefer the column-based understanding for convolution. But of course, you're very entitled to also consider the output-driven approach, where you just consider a fixed value of t here. Then to get g, you've then got to do this rather awkward reversal of the kernel, shift it to t, take it point by point multiplication with f, and then sum it up. It's all the same thing. Hope that's been useful. Thanks for listening.